Our lesson 7.2 is about calorimetry. If you are new to this channel, please do not forget to subscribe, hit the bell, and do some comments. I post educational videos at least twice a week. So let's get started. Our lesson 7.2 has the following goals: to define heat energy and to calculate heat capacity. Goal number 2, to describe the technique of calorimetry and solve problems involving calorimetry and interpret heat exchanges. Heat energy and heat capacity calculations. Heat is a familiar manifestation of transferring energy. When we touch a hot object, energy flows from the hot object into our fingers, and we perceive that incoming energy as the object being hot. Conversely, when we hold an ice cube in our palms, energy flows from our hand into the ice cube, and we perceive that loss of energy as cold. In both cases, the temperature of the object is different from the temperature of our hand, so we can conclude that differences in temperatures are the ultimate cause of heat transfer. The amount of heat transferred from one system to another system is given by this equation: Q equals M times C times delta T, where Q equals the heat transferred in joules or calories, M is the mass in kilograms or grams, C is the specific heat in joules per kilogram per degree Celsius or calories per gram per degree Celsius. Delta T is the change in temperature, that is final temperature minus initial temperature. And we note that 1 calorie is 4.186 joules, and 1 calorie per gram per degree Celsius equals 4.186 joules per kilogram per degree Celsius. Specific heat. Specific heat is the amount of heat required to raise the temperature of 1 kilogram or 1 gram of a material by 1 degree Celsius. For example, the specific heat of water is 4,184 joules per kilogram per degree Celsius, or the specific heat of sand is 664 joules per kilogram per degree Celsius. The greater the value of the specific heat, the greater is the amount of heat required to raise the temperature of 1 kilogram of material by 1 degree Celsius. This is why land heats up quickly during the day and cools quickly at night, and why water takes longer. Table 1 shows the specific heats of some common substances. Let us do some examples now. Example number 1. Determine the heat energy required to raise the temperature of 100 grams of water from 20 degrees Celsius to 85 degrees Celsius. The specific heat of water is 4.184 joules per gram per degrees Celsius. Solution. Using the formula Q equals M times C times delta T, substituting the values and simplifying, we have 100.0 times 4.184 times 85 minus 20. That is final temperature minus initial temperature. The result is 27,196.0 joules. Example number 2. Aluminum has a specific heat of 0.902 joules per gram per degree Celsius. how much heat is lost when a piece of aluminum with a mass of 23.984 grams cools from a temperature of 415 degrees Celsius to a temperature of 22.0 degrees Celsius. Solution. Using the formula Q equals M times C times delta T and substituting the values, you have 23.984 times 0.902 times 22.0 minus 415.0. This is final temperature minus initial temperature. So the result is negative 8,501.992 joules. The minus sign indicates that it is a cooling process or that energy is going out of the object. Example number 3. The temperature of a sample of water increases from 25 degrees Celsius to 98 degrees Celsius when 24,500 joules are applied. The specific heat of the liquid is 4.184 joules per gram per degree Celsius. What is the mass of the sample of water? So, from the formula Q equals M times C times delta T, and solving for M equals Q over C times delta T. Substituting the values is 24,500 divided by 4.184 divided by 98 minus 25 equals 80.21 grams. Example number 4. 850 calories of heat are applied to a 250 gram sample of liquid water with an initial temperature of 13 degrees Celsius. Find letter A, the change in temperature, and letter B, the final temperature. The specific heat of liquid water is 1 calorie per gram per degree Celsius. Solution. Using the formula Q equals M times C times delta T, letter A, solving for delta T equals Q over M over C equals 850 divided by 250 divided by 1 is 3.4 degrees Celsius. Letter B, from delta T equals T final minus T initial, solving for T final equals delta T plus initial temperature. So it is 3.4 plus 13 equals 16.4 degrees Celsius. What is calorimetry? Calorimetry is the quantitative measurement of heat. It measures the transfer of energy from one system to another system caused by temperature differences. A calorimeter is a device used to measure the amount of heat involved in a chemical or physical process. For example, when an exothermic reaction occurs in solution in a calorimeter, the heat produced by the reaction is absorbed by the solution, which increases its temperature, as shown in figure A. Exothermic reactions are reactions or processes that release energy, usually in the form of heat or light. When an endothermic reaction occurs, the heat required is absorbed from the thermal energy of the solution, which decreases its temperature as shown in figure B. The temperature change, along with the specific heat and mass of the solution, can then be used to calculate the amount of heat involved in either case. Endothermic reactions are reactions or processes that absorb heat energy from the surroundings to form products. Calorimetry problem calculations. Consider the following scenario. Suppose we initially have a high temperature substance such as a hot piece of metal M and a low temperature substance such as cool water W. If we place the metal in the water, heat will flow from M to W. The temperature of M will decrease and the temperature of W will increase until the two substances have the same temperature. That is, when they reach thermal equilibrium, as shown in figure B. If this occurs in a calorimeter, ideally all of this heat transfer occurs between the two substances, with no heat gained or lost by either the calorimeter or the calorimeter's surroundings. Under these ideal circumstances, the net heat change is zero, or the heat lost by the metal plus the heat gained by water equals zero. This relationship can be rearranged to show that in magnitude, the heat lost by the substance M is equal to the heat gained by substance W. Or in equation form, the heat lost by the metal equals the negative of the heat gained by water. Example number 5. A piece of metal weighing 59.047 grams was heated to 100.0 degrees Celsius and then put it into 100.0 ml of water, initially at 23.7 degrees Celsius. The metal and water were allowed to come to an equilibrium temperature, determined to be 27.8 degrees Celsius. Assuming no heat lost to the environment, calculate the specific heat of the metal. Specific heat of water is 1.00 calorie per gram per degree Celsius. Solution. The heat lost by metal equals the negative of the heat gained by water, or Q sub Lm equals negative of Q sub GW. From Q equals M times T times delta T, we have a quantity M times T times delta T of the metal equals negative of the quantity M times T times delta T of the water. Or if we distribute the subscript M to each term in the parenthesis and also the subscript W to each term in the parenthesis, we have M sub capital M times C sub capital M times delta T sub capital M equals negative M sub W times C sub W times delta T sub W. Rearranging the equation to solve for C sub M, we have C sub M equals negative M sub W, C sub W, times T delta T times sub W divided by M sub M divided by delta T sub M. Here we are given the following values. The mass of water is 100 ml, which is also the same as 100 grams. 1 ml equals 1 gram of water. The specific heat of water is 1 calorie per gram per degree Celsius. The change in temperature of water is final temperature minus initial temperature, 27.8 minus 23.7 equals 4.1 degree Celsius. The mass of the metal is 59.047 grams. The change in temperature of the metal is final minus original. So 27.8 minus 100.0 equals negative 72.2 degrees Celsius. So, substituting the values and simplifying, the specific heat of the metal is 0.096 calorie per gram per degree Celsius. Example number 6. A 360 gram piece of rebar, this is a steel rod used for reinforcing concrete, is dropped into 425 ml of water at 24.0 degrees Celsius. The final temperature of the water was measured as 42.7 degrees Celsius. Calculate the initial temperature of the piece of rebar. Assume that all heat transfer occurs between the rebar and the water. There is no heat exchange with the surroundings. Specific heat of steel rebar is 0.490 joule per gram per degree Celsius, and for water is 4.184 joules per gram per degree Celsius. So, solution, the heat lost by steel equals the negative of the heat gained by water. From Q equals MC delta T, we have MC delta T of steel equals the negative of MC delta T of water. Or distributing the subscript S to each term in the parentheses on the left side and the subscript W to each term in the parentheses on the right side, rearranging the equation to solve for delta T sub S, we have delta T sub S equals minus M sub W times C sub W times delta T sub W divided by C sub S divided by M sub S. Here, the given values are mass of water 425 grams, specific heat of water is 4.184 joules per gram per degree Celsius. The change in temperature of water is 42.7 minus 24.0 equals 18.7 degrees Celsius. The mass of the steel rebar is 360 grams and the specific heat of the steel rebar is 0.490 joules per gram per degree Celsius. So, substituting the values and simplifying, we get delta T sub S equals negative 188.51 degrees Celsius. But we are not done yet because we are required to calculate the initial temperature of the piece of rebar. So, since delta Ts equals final temperature minus initial temperature of steel. Solving for the initial temperature of steel, this is equal to delta is final temperature, which is common to water and steel, minus change in temperature of steel. So, substituting the values, you have 42.7 minus negative 188.51 equals 191.21 degrees Celsius. Example number 7. A 248 gram piece of copper, initially at 314 degrees Celsius, is dropped into 390 ml of water, initially at 22.6 degrees Celsius. Assuming that all heat transfer occurs between the copper and the water, calculate the final temperature. Specific heat of copper is 0.385 joule per gram per degree Celsius, and for water is 4.184 joule per gram per degree Celsius. Solution, using the same formula, heat loss by copper equals negative heat gain by water. Substituting the values, simplifying, we have M of copper times specific heat of copper times delta T of copper equals negative of the mass of water times specific heat of water times delta T of water. We let T sub F as the final temperature of water and copper. Here, the mass of water is 390 grams, specific heat of water is 4.184 joules per gram per degree Celsius. The change in temperature of water is final temperature of water, T sub F, minus initial 22.6. The mass of copper is 248 grams. The specific heat of copper is 0.385 joules per gram per degree Celsius. And the expression for the delta T of copper is the final temperature minus its initial, or TF, minus 314. So, substituting all these values, collecting similar terms because our unknown is final temperature, and simplifying, we get T sub F equals 38.73 degrees Celsius as the final temperature of water and also the final temperature of copper. Example number 8. A 59.7 gram piece of metal that had been submerged in boiling water was quickly transferred into 60.0 ml of water initially at 22.0 degrees Celsius. The final temperature is 28.5 degrees Celsius. Use this data to determine the specific heat of the metal. Use this result to identify the metal. Specific heat of water is 4,184 joules per kilogram per degrees Celsius. Again, the heat lost by metal equals the negative heat gained by water. Or the mass of the metal times specific heat of the metal times delta T of the metal equals the negative of the mass of the water times specific heat of water times delta T of water. Rearranging the equation to solve for specific heat of the metal, we have Cm is negative mW, Cw delta Tw divided by m sub m divided by delta T sub m. Here, we are given the following values. Mass of water, 60 grams. Specific heat of water, 4,184 joules per kilogram per degree Celsius. The change in temperature of water is 28.5 minus 22.0, 6.5 degrees Celsius. The mass of the metal is 59.7 grams. The change in temperature of the metal is final minus initial. The final temperature is 28.5 and the initial temperature is 100 degrees Celsius because it is initially submerged in boiling water. So the initial temperature was 100 degrees Celsius. Substituting the values and simplifying, we get C sub m equals 378.57 joules per kilogram per degree Celsius. If we compare this with values in table 1, our experimental heat, specific heat, is closest to the value for brass, which is 375 joules per kilogram per degree Celsius. So we identify the metal as brass. Thanks for watching. Please do not forget to subscribe.